Ultrasound is dolphins, bats. Okay, these are some of the species you can hear the sound ranges. Even rhinos. Rhino. Rhinoceros. Okay. This we did in the last class. Okay. Then let's see how bats, dolphins use ultrasound. So basically, ultrasound is most energetic sound wave. Why so? Because it has the higher frequency. Frequency is associated with energy. Sense, awareness. Highest frequency. So therefore, it can travel much longer distances to the atmosphere. High directivity. And can travel much longer distances to the atmosphere. Okay. So much deviation. So atmosphere is not able to absorb it or dissipate it. It can travel longer distance due to high energy it produces. So has high penetrating power. More energy, so it will go much deeper. Okay. So let's discuss applications of the first application is sonar. Did we discuss sonar application last class? completely leave them with this. And the application will uses where this ultrasound is used. It is used in sonar device. Sonar stands for sound, navigation, and ranging. Stands for sound, for SO, navigation, and ranging. Okay. Sound, navigation. So navigation is basically a safe direction. And ranging is basically estimation of distance of obstacle. Distance of obstacles. Okay, this is what it is. So, for example, suppose we have a ship. Right? Okay. So let us say it has a sonar device. A sonar device on the deck. And if we are on, wherever it is placed, has to be placed at a convenient location. Let us say it is placed. And so the captain sees some tip of the iceberg. Iceberg. So the iceberg property is it lies almost 90% underwater. Visible part is very small. And you don't know how much spread out it is under water or below the water. Right? So if the captain continues to sail the ship, thinking that he can avoid few meters and then navigate the ship from there. But he may misjudge it. Okay, and the propeller of the ship might go and hit the spread out portion of the iceberg, which may cause damage to the ship. Okay. So what's the way out? Way out is From sonar device, the signals are sent in all directions. And from the reflected signals, okay, the captain will be able to figure out the obstacle, okay, that it is not safe. So then he will change the angle, same direction, or he will choose a proper angle to turn. Not only that, so from the formula, V is equal to 2D by T because it is echo. It's working on the principle of echo or reflection of sound. So T into T by 2. So we will know how far is the obstacle. Accordingly, he will. So this is in judging the distance also of the obstacle or threat. Likewise, if somebody has to calculate the depth of sea, and here you can send it and the reflected ray. Sonar device will be able to calculate the time of reflection or time of echo. So here also D is equal to V1. And V is the speed of sound in sea water or the medium. So all those data is available. Just you measure T and you can calculate the distance. So this is ranging. Okay. And once you have the range of the obstacle, then you can choose the direction, same direction to travel. That is navigation. Okay. Is that clear? So different location, the sea depth will be different. So you may keep checking, like whenever you are sailing in a different region, the sea depth could be different. All those things can be. So this is one part. So the second part is, second application is cleaning of machine parts. So how the machine parts can be cleaned? So let's say you have a delicate piece of electronics, right? Like some components of the watch. If it is open and you want to clean it, then how can you? You can't brush it like this. These are so delicate. So what you can do is, it can be soaked into some soapy solution or detergent. Okay, and then in that solution, you can project ultrasound wave. That will cause the water to vibrate. Okay, because of that, it will shake the dust out of it. Okay, that's what. So the dust will be detached. So this way you can clean the machine parts. There may be machines which are like odd shape, where it is difficult to reach. Let's say there is a spiral uh, part which is spiral in shape, so you can't reach it directly. But the soapy solution would, and with the vibrating water, okay, it will detach on the dirt which is there inside. Okay. So this waves will force the dirt particles out of the machines. Small miniaturized components. Is that clear how it works? Then in the medical field, what are the applications in the medical field? So second was cleaning of machine parts. Okay. So in this case, it was only solution. You may have some redundant here. Let's say these kind of components you have. Some delicate electronic parts, etc. So then you basically project ultrasound waves. they are directed in the filter, which will then produce vibration, which will detach the current. Okay. Okay. Third gets attached. Attached. Paused. Third. Solution. Right. Isn't it? So this is what happens. Third application of ultrasound wave in the medical field. So here you have what is called as ultrasonograph. You must have heard about ultrasonography. In this technique, what is done? The images of internal organs are obtained. Okay. It is used for imaging of internal organs, such as liver, gallbladder, the uterus, right? So all those things. Then also kidneys, right? Kidneys, intestine. So you can actually send ultrasound waves, and from the reflected sound waves, when they are processed by a computer, these images can be created. So from the images, we can figure out the state of the internal organ. So by comparison with the images of organs of healthy person, the level of deterioration can be figured out. Okay, you have ultrasonography. If the image is only done of heart, it is then called echocardiogram. Okay, so such thing. What other things can be done? Status, growth status. Oh, babies. Fetus. Pregnant. Okay, this also live status can be checked from the reflected ultrasound waves. So which is less damaging because these are only sound waves. So these are not damaging to the fetus. It can also be used in treatment of kidney stones. treatment of okay, so what happens is the kidney stone is forms over a period of long time. So it's not that it is at initial stages it is not very hard. So till a certain level of hardness, when it is exposed to ultrasound wave, it can break it into granular pieces. Okay. So it can be done only till it has not reached a certain critical hardness level. Before that, otherwise only surgery is the option. Okay. So at that stage, even kidney stones can be broken, and then it can be flushed out with the passage of urine. All those things are possible. If the fetus has heart disease, that also can be checked. Okay. Then fourth, it can be ultrasound waves can be used for welding of plastic. So far, you must have seen welding of iron sheets, right? But even plastics can be welded together. When on two plastic sheets, some ultrasound is fast. When in industries, it is also used to detect flaws in welding. Welding is welding. So ultrasound is used to detect flaws in welding. Okay. So wherever the welding is not proper, it will be reflected back from there. Okay. Also, there may be some uh, metal blocks, right? If there are cavities inside, detect flaws in welding. Can also be used to detect cavities or cracks inside metal blocks. So when these bridges etc. are constructed, okay, sometimes in the foundation, metal blocks are used to give strength to the bridge, right? But outside it may appear to be a solid one piece, but there may be crack inside. So when the ultrasound wave is passed through the metal block, inside wherever there is a cavity or crack, it will be reflected back. Okay, so that can easily be detected. So how the process works, that is not in the scope of discussion. You can just know that what are the applications. So detect cavities, cracks inside metal blocks, right? Pipes. So you must have seen on the sides of the highway, large pipe, traveling. So they might be oil pipe, gas pipe, okay, or water pipe. Have you seen? Very big diameter pipes are on the sidelines of the highway. You might see sometimes. So if there are any cracks in the pipe, even that can be detected using ultrasound. Okay, so with this, we've completed the chapter. If you have any questions, you can ask. or else we'll go to classwork dividers or review questions. So I'll run through the review questions because some of you missed the theory part, okay? So we'll try to cover it during this talk. Okay, so first question, how is sound produced and propagated in air? In air. How is sound produced? It is produced by it is produced by vibrating objects or vibrating bodies. How does it propagate in air? Compression and rarefaction. So sound travels like this. It produces a series of compression and rarefaction in the medium through which it travels. So compressions are the region of high pressure and density. Rarefaction are region of low pressure and density. And during the sound propagation, the particles of the medium oscillate parallel to the direction of propagation of sound. That's why it is a longitudinal wave. What kind of wave is sound wave? Longitudinal wave. And it is also mechanical wave because it's mechanical longitude. Because it requires medium, so it is mechanical. And since the particle moves parallel to the direction of propagation of sound, it is also called longitude. List two factors which affect the speed of sound in air. Temperature, density of the medium. Ultimately, it's density because temperature also varies the density. And the elastic property. Okay, elastic property. If the medium is more elastic, the speed of sound will be more in that. Like solid is more elastic than liquid and gas. And it's not like rubber is more elastic than metal. No, not like that. Rubber is not more elastic than steel. I discussed what is the meaning of elastic. Like if same amount of force is applied to a steel and rubber, which will be able to regain the shape? Steel. That's why steel is more elastic. That's why the speed of sound will be more in steel or solid as compared to air or gas. Then we already defined frequency, time period, wavelength, and amplitude. Quickly, what is frequency? Yes, time period. Correct. Time for one vibration or one oscillation. What is one oscillation or one vibration? Yes, one pull to and fro motion of the oscillator. What is oscillator in case of sound wave? When it is traveling through air body. The one which is carrying the energy from molecule to molecule. So only the energy is transported. Molecule is not moving. It is only oscillating around its main position. So what is moving is disturbance or energy. What is wavelength? Yes, distance traveled by the wave or the distance traveled by the disturbance in one time period. Because one time period takes for one oscillation. And what is the amplitude? Amplitude is maximum displacement of the oscillating object from its mean position during wave motion. So maximum displacement from its mean position. On what factor does loudness of sound depend? It is depend on amplitude. If the SI unit of amplitude, frequency, and wavelength. Amplitude is distance. So frequency is 1 by t, or which is per second or hertz. Per second is hertz. Okay. Wavelength, meter. Very close. Okay. What is the tone I discussed it. Tone is the sound of unique frequency, single frequency. Tone is the sound of single unique frequency. Just scribble it next to it if it is not written. Tone is the sound of unique or single frequency. Draw graphs to show a loud and soft sound. So loud sound will have bigger amplitude, soft sound will have smaller amplitude. So this is the loud sound. This will be a soft. Okay, that's good. All right. Then define echo. Yes. After the original sound ceases to exist. So echo is when two distinct sounds are heard. The reflected sound and the original sound. So after the original sound ceases to exist, the reflected sound. That is differentiate between infrasonic and ultrasonic sound. Ultrasonic is gigahertz and ultrasonic is greater than 20 kilohertz. Correct. Are both audible to human? Then give an example. Who can hear infrasound? Whales, elephants, rhinos. So they can hear as well as produce. They can communicate by producing such sound. What about ultrasound? Bats and bats. Okay. That's give full form of sonar. Sound and range. Sound navigation and range. Explain the propagation of sound in air. Already done in question 1. Write an experiment to show that sound needs a material medium to travel. Which experiment? Belgia. Are you able to understand? Did I explain it to you? Okay, so Belgia experiment. State the condition for echo to be heard. Huh? Yes, the reflected sound must reach the listener at least after 0.1 second or more. And should be how much? Yes, around 17.2 meters. Good. Then explain any two uses of multiple reflection of sound. Stethoscope, trumpet, then shelleye, then curved ceiling of an auditorium. All of those. Because that will fall in multiple reflection of sound. Okay, we have some numericals around 9. I'll quickly give you the logic and some you may answer yourself. Okay. So what are the formulas in this chapter? E is equal to mu lambda, that's velocity of sound. Also velocity is distance upon time, right? And this can be lambda by time period, whatever is applicable. And for echo, distance of echo, it will be 2 by wherever you have echo, right? So this is how it is. Is that clear? Capital D is time period, T is time duration. So this is the general formula for speed or velocity. And this is speed of sound wave. Okay. In terms of its frequency, wavelength and time period. So these are the only three formulas that I use. So question 1. Password developments. This is on page number 81. What do you have? What is the amplitude in the given wave? See the diagram. 2 centimeter. What is the amplitude? Wave given to you is, and this is the amplitude, right? And it is given as 2 centimeters. So this is mean position. So maximum displacement is 2 centimeters. So that is the amplitude. Correct. So sound wave has a frequency of 5 hertz and wavelength of 20 centimeters. How long will it take to travel 1 kilometer? So here B is equal to distance upon time. Therefore T is equal to distance upon velocity. And this will be mu lambda. Correct? So V is mu lambda. What is distance given to you? 1 kilometer. So 1 kilometer is basically 1000 meters. To travel 1000 meters, the sound of wavelength 20 centimeters, and frequency 5 hertz. This is 5 hertz. And what is the wavelength? 0.2 meter. This will be 5 per second. What is the unit of frequency? Hertz or per second. So this second goes up, meter gets cancelled. So what do we get? It is 1000. It will take 1000 seconds. That's the answer. Everybody understood the question, right? So here you have to find distance of reflecting surface. So you have to use B is equal to, it's an echo question. So you have to use third form. V into T by so what is B here? 342. T given is 1.5 divided by 256.5. This is what you should get. 256.5 meters. So this is given as answer of question 4. In your book, that is a mistake. Right? So question 3 answer is given in question 4. So it is on 1 below. Then question 4. So time of echo is 3 seconds. What is the distance? Again, you have to use the same formula. So here is 315 times 3. So how much is this? So it's just Why 35? Again, answer to question 4 is given in question 5. What is question 5? This also same formula, depth T. Okay. All of these are echo questions. So T given is 4 seconds, speed given is 1531. So this will be 2 times 200 plus 3062. So wherever you need help, just stop me and ask for. Are you understanding so far? Sure? Okay. Then we have question number 6. A wave of frequency 100 Hz, what is the time period? So we know that there is relation between frequency and time period. Right? Correct? So what is time period? T is equal to 1 by 100. So this will be how much? This is a time. Question number 7. What is the wavelength of the wave in a given diagram? So, what is the diagram given to you? This is the diagram. Right? So it has 3 parts, right? And this length is given as 6 meter. Correct? So what is the wavelength? What wavelength is only this much. Wavelength is distance traveled by one oscillation. So if it is 3 parts, it will be 2 plus 2 plus 2. That means wavelength is equal to 4 meter. Also find its frequency if it travels with the speed of 3 meter per second. So what is given here is V is equal to 3 meter per second. So we have wavelength and velocity. So what is the frequency? E by wavelength. 3 divided by 4. Okay, so it will be 0.75. This is what it is. Correct? Speed is given 3 meter per second. And this is given this distance. The wavelength is also kind of distance. Okay, with this we come to 8th question, which is what? So what is a slinky? Any idea? Do you know what is a slinky? See, this is a slinky. You must have played in childhood. You hold that thing and do like this, right? Slinky. So it working. You've seen this. That's what it is.
This is a Slinky, and this is the world's first infinite Slinky stair shift. And I made it because as a kid, I would always try and see how many stairs I could get my Slinky to climb down. With my rhythm exactly always maxing out at 7 or 8. I decided now that I'm an engineer, it's time to avenge this childhood frustration and set an unbeatable world record. The thought I had was using a treadmill tilted at just the right angle. The problem with that is there was very little repeatability because the landing surfaces were inclined unlike actual stairs. On that issue, I tried an actual
Wave motion.
which a little better. The steps wasn't ideal and the speed was a little. And after we decided to make our own prototype of an escalator, I could turn with a hand crank. And that's the prototype.
Wave motion. It's like
This festive season, bring home Honda, bring home joy. Visit your nearest Honda to take a dealership today.
see. So present traveling. Is the spring leaving its position? No. Leave the distance. Leave the distance travel. So multiple compression time where fractions are formed. If you don't focus on the compression, you will see that even rare fraction is there. So either compression or rare fraction. You can focus on any one. And you can zigzag it like this also. Next video. This is the direction of propagation of disturbance. Whereas this is oscillating at its mean position. Spring is not moving, only the disturbance. Right. So slinky is a good way to feel the wave motion. You can create a transverse motion also. Now the friction is across, but the disturbance is still reaching the other end. So this was the example of transverse motion. You see, direction of vibration, but disturbance is going forward. So this is transverse. Okay, so if you make good use of YouTube, there are many fun things that you can learn things easily. But don't get lost. Like stick to the topic. It will take you from one topic to other topic. A lot of it may not be of your level, maybe advanced. So you need to know the limit where it is switching to an advanced level. So it can, while in your search, you can mention your grade. Okay, wave motion 9 CBSE or 10 CBSE, whatever. So it will only give you the relevant videos. Okay. So slinky is that spring basically. So we were discussing question number 8. Longitudinal wave produced on a slinky, the first video. Wave travels at 50 centimeter per second. So what is given to you in this question? What is 50 centimeter per second? Velocity. So which is basically 0.5 meter per second. And frequency given to you is 10 hertz. Or 10 per second. Hertz is the honorary unit. Hertz is the name of the scientist. Okay. And actual meaning of hertz is per second, 1/3. Okay. So when you are doing calculation, this makes more sense. So that will be deducted. What is the minimum separation between two adjacent positions where the link is most compressed? Now, distance between two consecutive compressions is nothing but wavelength. Either compression or two consecutive rarefactions. So basically, you are supposed to find wavelength here. The question is asked indirectly. They are not asking you directly how to find the wavelength. They are asking you distance between two compressions. Okay, with the sling. What is the answer? So, from here, wavelength is V by mu. So it is 0.05 meter or 5 centimeter. Okay, this is the answer. So this answer is not given in the question. That's the mistake. All the answers are of previous question. So, and then the answer given is of question 9. So question 8 answer is this. What is the 9th question? Again, here frequency and wavelength is given. How long will it take to travel a distance of 2 kilometers? So whenever you have to find the time, time is distance upon velocity. And then distance upon wavelength. Okay, this is how you'll find the time to travel the given distance. So what is the distance given in the question? 22 centimeter, that is 0.22 meter. The frequency given is 1500 hertz or per second. And lambda is how much? Oh, lambda is 0.22. And this is 2 kilometers, that is 200 or 2000. You can solve this. When you solve this, you should get it as 6.06. Because what it will be, it will be zeros into that one. This is 211 times 5. So this is 200 by 33. Find out how much it is. Would be 6.06. Okay. So with this, we come to end of the physics portion, the science syllabus. So now we'll meet only on request. Okay. Whenever you book extra lecture. So in the meantime, I wish you all the best. So study well. ठीक है? And do attend doubt sessions and whenever you need, book an extra lecture. Okay, all the best.